Good morning and welcome to part 4 of Salford Systems series on the evolution of regression from OLS to GPS, Mars, CART, TreeNet, random forest, ensembles of tree methods. Thank you for joining us for this fourth of our sessions. Most of today's session is intended to be illustrating the methods that we spoke about 2 weeks ago, but hands-on, and we encourage you to download the software, work with the example data set, work with your own data, and get a feel for how these techniques work. So, as you recall, we went through some classical regression. We went to the modern generalized lasso. We spoke about Mars, then CART, the ensemble methods of the bagger, random forest, stochastic gradient boosting. And we didn't talk about hybrid methods, so we're hoping to squeeze that into the session today. So remember, we're working with the Boston housing data set. This is just an example. We don't want to draw any hard conclusions from results that we see here. These are strictly illustrative. The only thing that matters, of course, is what works in your data. But it's a good place for us to have common ground on a data set that everyone can understand. Okay, so recall we were looking at some of the mean squared error results that we were getting, or prediction squared error that we were getting on the 20% randomly selected set-aside data. We're going to show you a little bit later how to actually mark that 20% random sample, so you could even try it with other software beyond the SPM that we've hoped you've downloaded. Okay, so let's go directly to the software now. And so what I'm going to do here is just open the file that we want to work with, and that happens to be remembered here. My apologies if some of what I do appears to be a little fast. The slides that we have prepared should be of greater assistance in allowing you to walk through slowly. We'll also make available the command line scripts in order to replicate everything that we've done here. Okay, so we see the data set that we have open, 506 records, 14 variables. The names are as they were named by the authors that created this data set around 1978 when their paper was published, and that's why the names are short. We'll go directly to modeling. So what do we have to pay attention to here? First, the dependent variable, MV, which is the median value of a house in the neighborhood that is the unit of observation, the 506 of these census tracts. All the other variables will be allowed to be predictors, so we don't have to explicitly specify that they are, but let's go ahead and do that just for the sake of showing you that it can be done. And the other variables we're ignoring, the other columns we're ignoring for now. We want to set the analysis method to CART, and that's what it should normally go to, but if you've used a different engine in a previous session, the software will remember that and open it up there. We want to make sure that we choose regression. CART normally will default to classification unless you indicate otherwise. So, okay, so we're really ready to go. We do want to make sure we've set our testing the way we want it to be. This is always going to choose the same 20% random sample for test given this data set, unless you say otherwise. And the way you would say otherwise is to go to the options and indicate that you want that random number, which is used, the seed, to generate this, to allow it to drift instead of always being reset to the way it was. It's a great convenience, of course, when you redo an analysis to know for sure that the random number seed is starting as it had previously. Now let's leave all the other items at default, hit the start button, and those are the results that we saw before. Okay, so hitting the summary button gives us the mean squared error on the test partition at 17.29. So now we want to see what we can do to improve on that via the use of ensembles. And we can do ensembles in a number of different ways. We actually have at least 4 different ways in which we can generate ensembles here. So the first thing that I'll do is I'll go to cart ensembles. This is the oldest of the methods. We actually introduced this into cart in 1996. It's there principally because it's always been there. It's not a bad place to start. If you go to the ensemble window, the only thing that you want to pay attention to here is that we've set it to bagging. We don't want to do any pruning. That's recommended for the bagger style of ensembles. And we do want to set this to 0.2, so that will give us the same 0.2 and the same partition that we had arranged before. So what does that mean? We have a test partition that's set aside, and now we're just going to grow unpruned trees via bootstrap resampling on the remaining training partition or learn partition, and we're going to grow 100 of those. So now let's just hit the start button. And away we go. By the way, you will notice that the other methods for ensembles are much faster than this. CART is a fairly sophisticated and elaborate piece of machinery. The other methods, random forests and the stochastic gradient boosting tree-net, are much more streamlined and will actually run faster. So what has happened over here? We grew the initial tree. That is a reference tree, and you can see it's the same as what we had before. It's a 9-node tree, and it actually was pruned in the same way that it was pruned when we ran that tree standalone, and that's called the initial tree for a reason, because that is for reference purposes. And then we have the remaining trees that were grown. And so you can see that these are showing number of nodes in the high 80s and 90s, and they are actually all growing to the maximal size that they are allowed to achieve given the terminal node limits that we had previously set. Let's just click on tree number 1 and you'll see what that looks like. This brings up the tree. All the trees are sitting inside of that ensemble, and you can access any of them. And what you'll notice if you go to a terminal node, there are going to be fewer than 10 records in each one, because that is the limit that we had set by default for splittability of a node. We could have changed that. We didn't for this round. Okay, so how did we do there? Well, this particular display doesn't give us the performance of the ensemble, but the classic data shows us how we did. And these are the performances for all the individual trees, and then we will have up here, we should have, I guess I'm going to have to go to the beginning. Well, anyway, let's just go ahead and take on faith what I've shown you over here in terms of our results, that our performance for the bagger was as we have indicated. Okay, let's go back to the live software, and let's try a different way for running our ensemble. And this time we're going to do it not via the cart ensembles, but let's do it via cart again, and we'll use the battery bootstrap. So let's add that there. Let's build 100 of these. We're also going to build a reference model. We're going to do no pruning. And now we're just going to hit the start button. Again, we've got our 100 trees that have been generated. And now, in order to see the performance, what we're going to do is the following. We're going to score using this ensemble of 100 trees. And what I'm going to do is I'm going to open up a data set which I previously created. It's the same as the Boston data set, but it's got a flag indicating which are the train and which are the test records. And we're just going to go ahead and now run a scoring there. And here we see our results, which have the mean squared error at 7.42 for this particular ensemble. Okay, let's go back to the original data set, which is the same, except that it doesn't have the flag that I was just talking about. Again, making sure that we've got regression set, and then we got testing set at 0.2. And now what we're going to do is move on to the next engine, which can give us these ensembles, and that's random forests. We'll start with random forests running in its default mode. So that's going to pick 3 records at random. For testing, we're also going to have the 20%, the same 20% held back. We don't need to do that. We have the option of letting out-of-bag data be our methodology of evaluating our performance. But here, we want to be able to compare results with previous runs. So let's hit the start button again here. You can see the speed advantage that comes from the streamlined trees. And here, if you can see it, that is giving us the mean squared error of 8.286. Not necessarily the best that we can get, because we just ran with all the control settings as they come out of the box. So let's go ahead and run a little bit of an experiment here. We'll go to the battery, which is a prepackaged set of experiments. Let's go to the experiment that varies the number of variables that the search mechanism is allowed to look at each node of every tree. So let's go with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoops. Let's make sure we get this right. We'll go all the way to 13. We don't have a shorthand in this particular version, but those are all the possibilities that exist. And now let's hit the start button. You can see we are now running 13 different experiments. Each one is a full random forest run. Each one is growing 500 trees, but each one is using a different control for the mechanism by which the tree is being grown. And we really can't guess in advance which one of those settings is going to do best on this data. So the only way to be sure is to experiment. So now it's assembling all the results, and let's see how we did. So what you can see here is mean squared error. It was not as good as it could have been if we selected only one variable. It also is not as good if we go all the way up to 13, but we have a sweet spot here at 4. Now I want to run one more experiment for you, which is relevant specifically to the regression. And that is, what is the right minimum node size. And this number, where we are allowed to split the nodes even down to a node that has 2 records in it, that's great for classification. It is not necessarily the right way to do things for regression. And so experimenting with different numbers here is ideal. We're going to set this to 5, and then I'm going to run the same experiment once more. But watch this. So first I'm going to hit a continue. I'm going to close this window here because it's collecting an awful lot of trees. And we want to not overwhelm memory here. And so now what I want to do is I'm going to go to my command log here, and I'm just going to rerun this set of commands. Why am I doing it this way? Well, I didn't want to type those numbers again, and I got this out of the command log. In case you didn't follow what I did, I'm going to show you once more. Let's just close this. Go to the toolbar. There is an icon with an L on it for log. Click that. That gives us the command equivalents of everything we've done so far. Then I went to the command that I was interested in, which is running the battery for random forests with different number of variables allowed at each node. And we'll just run this subset of the commands with Control W. And let's see what happens now that we are not allowing the nodes to split quite as small as we had previously. Again, it takes a few moments to assemble all the results. And what you can see here is now we're actually getting slightly more favorable results, and we're being recommended to work with 6 of the variables instead of 4. Okay, so recalling what random forest is, we're building random trees. How? By introducing randomness into how the split variable and the split point is being selected. And we're also randomly selecting the rows, in this case with bootstrap resampling, so that is a random form of weighting of the records in the data. So we have randomness in the rows and randomness in the columns. Okay, now let's go on to the next methodology for creating ensembles of trees. And here we're going to go to TreeNet, which is stochastic gradient boosting. So with stochastic gradient boosting, the controls here are the number of trees. Let's make that 1,500. Well, let's make it 2,000. We're going to leave everything at the moment unchanged, except that our method of building the loss function will be least squares. We have other options. We're going to come back to those momentarily. Everything else we're leaving in its default mode. Let's hit the start button. You can see those 2,000 trees were built very quickly. And we're getting a very good MSE here. That number is down at now 7.39, quite a bit lower than what we saw certainly for the single engine methods. Let's also recall one of the nice features of the gradient boosting methodology are these dependency plots. We'll select all the variables. We'll just do one-way dependency plots and show them all. So these are graphs that are based on simulations. These are predictive simulations that show what would happen on average if the percentage of lower socioeconomic status people increased from its low all the way through to its maximum value by using the actual data and running a simulation on every record of the data set and then averaging the curves. So that's what we see here. If you click on any one of these, double click, and bring up the individual graph, you can do many more things with this graph. I'll just turn the markers off. You can put smooths through here. You can look at the scatter of points the data that was actually underlying this, predictions made by the model, etc. Okay, let's put that aside for the moment and go back to building a better model. So I'll just close all those. Let's go back to the TreeNet methodology, and let's go to the batteries and move down to what's called here TNReg. So that's going to be gradient boosting regression methods. And we're going to run this regression model 6 different ways. There's many more that we could run, but this is a good start. So when we get the results, I'll explain what it is that was just done. So again, you can see how rapidly we're flying through this. And on the machine that I'm using, I'm not making use of multiple cores. You may very well be in a situation where you could. So this is the regression model in which the loss function was least absolute deviations. Since we're looking at mean squared error, you might think that making LAD the loss function isn't necessarily a good idea. However, sometimes it is the method that gives us the best performance on test data. So it's very worthwhile experimenting. Then here we're looking at least squares, and you can see that using a least squares loss function gives us a model that performs slightly worse on the test sample squared error than using LAD as the loss function. But even better are the Huber models. The Huber, remember, is a hybrid between least squares and least absolute deviation. A certain percentage of the errors are squared. That's the smaller errors. And then the largest errors, the increment to the loss, is not squared. It's simply the absolute value. And so you can see here, this is where 98% of the errors are squared, the lower 98%. Here, the lower 95%. There, the lower 90%. There, the lower 85%. You can see the default when you go to the Huber is the lower 90%, that breakdown parameter, and we're finding that 95% performs a little bit better. Of course, you could do a grid search that is much finer and make these in steps of 0.01 instead of 0.05 as we did here. But this is just the convenience for allowing you to get an idea of what might be better. Here, the minimum mean squared error that we're getting on the test sample is now at 6.7. Okay, so we have now covered the ensemble of trees, the ensemble of cart trees via the battery bootstrap. We have looked at random forest, and we've looked at TreeNet. Let's do one more thing with TreeNet before we leave TreeNet all by itself, and that is, let's go to the advanced TreeNet model. Well, let's go here first to random forest, and we're going to make TreeNet simulate random forest. And what we're going to do here on the advanced tab is we're going to set this to 6, just borrowing from what we learned in the RF models. And other than that, we'll make sure that the testing is set the way we want it. And we want to make sure also on TreeNet, because we're going to be growing RF style trees, we want these to be big. So let's make this 500. This is the maximum number of nodes in a tree. All right, so let's see what, and let's make sure we've got this set up correctly. Let's hit the start button. In this case, we're using the gradient boosting machinery, but we're not using it to do gradient boosting. We simply grow a tree, don't adjust the dependent variable, but make the other changes, and then repeat the process. So you can see the flatness of this curve here, which is not surprising. And now let's look at what our final performance here is. Well, not so good at about a 10.4. But what's nice about using this methodology to simulate the random forest methodology is that I can get the plots. So if I do the same thing over here, select all, and then get our plots, you can see that these curves actually look pretty similar. So there's no surprises here, just in the details do they look a little different. Okay, so now I'm closing some windows here just because some of these runs ran very many models, very many trees, and I don't want to overwhelm the memory resources of this machine. So now let's go on to the next step, which is the combination of trees and the generalized lasso. So we have our dependent variable here. As before, it is regression. We're going to make sure that our testing is set to the way we want it to be. And now we're going to go to rule learner, and we're going to ask this methodology to do just compression. How is that going to work? We're going to let every tree, let's make sure that we've got this right. We don't want random forest now. What we want is these squares again, or let's use our ideal blend here with a 0.95 there, since that was giving us our best performance. And then we're going to set this back to the 6-node tree. So what are we going to do? We're going to build a conventional gradient boosting model. It could have up to 2,000 trees in it. Each of the trees is trying to correct the errors of its predecessor, but each tree is therefore also a device that takes the raw data as input and produces an output. And that means that that output could be considered a new column of data. We're going to create all those new columns of data, and then we're going to run a generalized lasso on those new columns of data. Why? Because by doing that, we are essentially picking and choosing from the trees that are in the ensemble and possibly ending up with a much smaller subset of trees and possibly even a better performance. So let's now click on Start and let that go. So the TreeNet part just ran. Now we have the post-processing. So let's talk about what just happened here. The red curve on this display is the performance of the TreeNet as it builds its model myopically from one tree to the next. And so it goes on and it hits an optimum at some 1,400 trees. The dashed curve is what happens when we start with those raw material of, we do start with the 2,000 trees by default, and then we use the forward stepping path seeking to simulate the lasso or other variations in the elastic net. And this is the best performance that we get from there. And we are now picking our trees much more carefully because we're no longer working myopically. We can see what the last tree was, and we see we very rapidly can get into the space of a relatively low mean squared error. Now, it still does not compare to the TreeNet performance, but it is now much lower than working with an individual tree. So let's have a look at the details of the second stage GPS. You can see the different elasticity methods and how they're working. And let's look at what the optimal MSE is on the test sample. That happens to be a lasso, and it picks 71 of the trees. And that gets us to a 7.12. Now that is not the best MSE that we've seen, but it's certainly a very attractive one, especially considering that it involves a much less complicated model. If we look over here at detailed solutions, we see some of our other options. There is an 8 coefficient model, that gives us a test MSE of 8.2. So that may be even more attractive if you're working in an environment where you have to develop as small a model as you possibly can. And that 8.2, of course, is vastly better than any of the methods that we showed in the earliest sessions. Okay, let's try another variation of these models. Again, I'm going to close these windows, as there's an awful lot of information packed into them. And let's again go to the rule learner methodology, but now let's choose not the compression of the gradient boosting machine. Let's instead do what's called extraction of rules. How do we do that? Every tree is made up of nodes, and every node has a definition in terms of the conditions that a record has to meet to end up in that node. So what we can do is take the definition of that node and create a new variable, which is a 0, 1 variable. Yes, the record meets the conditions of that node, or no, it does not. If we do that for 2,000 trees, and we have typically 10 of these nodes inside of each tree, we're going to have 20,000 of these variables that will be constructed. I'm going to do one other thing. In GPS, I'm going to say, don't build me a model with more than 400 variables selected. Why am I doing that? Because if you recall over here, I am going to make 20,000 of these variables available, and I don't want the methodology to search all 20,000 variables in every forward step. So by setting it to 400, we allow ourselves to move much faster, but at the same time, we're probably not preventing ourselves from finding the model that we're looking for. It's up to you to decide what that limit should be, and if you have no time constraints, well, you might not want to put that limit there at all. So, otherwise, we are ready to go. So let's just hit the start button and wait for the results. So again, first the TreeNet model is built. Then we've constructed the 20,000 indicators, and we're now going through the elastic net variations, including the sub-elastic net compact model, looking for the smallest possible model we can get. And let's see what happens here. This curve will often look somewhat distorted because I've set a limit of 400 out of 20,000, and it shows me the path all the way through the 20,000 for the TreeNet, because the TreeNet does actually use all 20,000 nodes. So let's go ahead and look at the rule learner details and look at all the curves. So these are the different performances, and again, we can see that some of the elasticities are much better than the others. The lasso is the winner. It wants to work with 226 of the nodes. It gets us with an MSE of 8.7. Now, you might ask, this sounds like it's a relatively strange model made up of these dummy variables and coefficients on them. Mostly, when we use this methodology, it is a regression method, but we're actually typically interested in the rules rather than in looking at this as a regression. So let's have a look at what the rules look like. So if you click on the rules on the main display, what you see is a ranking of the rules. It tells us which tree the rule came from and which node number. So you can see that there is enormous flexibility here, and there is certainly no constraint that we pick something from the first tree. And in fact, if you look down here, the first tree doesn't appear to be anywhere in the list of the top 30. We can scroll down to see if one of the earlier trees does show up. It doesn't really matter at this point. This is all just raw material in order to try to build a model. But here's the statement of the rule. This is a statement that says that if the distance is greater than 1.4 and from the centers of employment, and the sizes of the houses are typically less than 7.4 rooms, then these are the results that we see. And so we've got this particular rule here is actually nailing the mean. Let's see a little bit more. Here we actually can see the details of the rules, and we've got a display which is sortable. So we can sort on the variables that are in the rules. Let's sort here on the test lift. Click twice, and what we get here is a rule that defines a subset of records in which the average value is 2.4 times what we see in the sample overall. But these node sizes are not very big, so maybe we should go down to one that's a little more acceptable, like at least we've got 10 records in the test sample here, and we've got a lift here of 1.7, and the rule is being based on the pupil-teacher ratio and the size of the houses, and that's it. And that gives us an indication of a factor that leads to higher valued neighborhoods, smaller classroom sizes, and larger houses. If you want to browse the rules, just click the next button, and away we go. Okay, so let's just take stock of what we have done. When you go to the model setup dialog, these are the engines that you can see. There is CART. We can see that that is not a bad place to start for a regression. After all, it's non-parametric. It knows how to deal with missing values. It knows how to deal with nonlinearity. The results will be independent of any transforms that preserve the order of the predictors. But it is not the most accurate model. Then we can get better models by either using the CART ensemble or within the CART framework by going to the batteries and then using the battery bootstrap. We also saw that we could use the random forest machinery, we could use the tree-net machinery, and then we could use the combination of the regularized regression and the trees in order to get our either greater insights into the data or superior results. So that brings us to the end of this particular walkthrough. I just want to discuss what might be happening next. So we have some plans for some future sessions. So let me indicate what those are. One will be the evolution of classification that will be parallel to this regression series. Another will be covering new methods of clustering, going beyond k-means and hierarchical clustering, at least as solo methodologies, but looking at new methods and combinations of old and new methods. We'll have at least one session on faster model development with staged modeling automation. We'll explain how partial automation and prepackaged experiments can cut substantial time from your modeling schedules. And then we're also going to have an overview of data mining for beginners. So in terms of next steps for our participants, besides questions that might be coming in, we do want to remind you that you can download an evaluation version of the software from our website. And so that's exactly the same version of the software that I was using today. Once you get it, that software will run for 10 days without a license. If you want to run longer, then simply request a license for us. We certainly invite you to do that, and that will allow you to go for a further 60 days. If there are issues that are specific to your environment that you want to talk to us about, please feel free to contact us, whether it's regarding working with very large data sets or with the specific capabilities and data mining engines that you are requiring. So at this point, I'm simply pausing to see if the questions that have come in are ones that we can cover in the few minutes that we have available. So, I'm looking at the questions here. One of them is, what is the role of steps in the IL process and the role of points? We don't have time to go into the details. These are the details that relate to how the forward stepping that is involved in the generalized path seeker traces out what would be the actual path of solutions when you run the elastic net. The main thing to keep in mind is that you just need enough points and enough steps so that you actually can arrive at an optimum. In the IL process, it may be less important to get that model truly optimized, the second stage. Very often, the earliest steps are going to be enough to get you into the ballpark of what you're looking for. But really, those numbers are just numbers which, if you increase them, the steps and the points, they may make your run take longer and use more resources in terms of memory as well. But other than that, there's really nothing to it. And so going with larger numbers is never going to hurt. There's a question about when you run the experiment to determine how many predictors should be included in the model. We chose the number with the lowest MSE. Where do you change the settings to reflect this? So I will show that here. This is a question about RF. So let's set the engine to random forest. Let's go to random forest. And you can see here the number of predictors considered for each node. So that is where you would change it if you're using random forest. If you're using TreeNet to simulate random forest, then after you've set this to random forest, you go to the advanced TreeNet tab, and that's where you would set the number that you are interested in using. What's the difference between the different type of batteries? How do you know when to use them? Let's go to a battery here. There's a brief description for each battery that you will see down below, and then there's extensive help on all the batteries. Every one of these is designed to run experiments about a different dimension of your modeling process. As you read through them, what you want to do is check whether the topic of a particular battery is of interest to you, and then run that. And you can think of the batteries as a recommendation for a set of experiments that you probably want to run. There is nothing wrong with running them all. It may just take you a little while to get the results. Our favorites are shaving. What shaving does is it allows you to remove variables from either the top or the bottom of the variable importance ranking list, and then to rebuild the model after variables have been removed. This controls how many variables are removed, and over here we control how many steps. And if you don't indicate the number of steps, then we're just going to go until we run out of variables. So that is a very effective method for trimming back a large number of predictors to a smaller set. So now there's a question about how do you use a model to make predictions on new data. Well, we did that a couple of times. So here's what you do. There's something called score. So if I just, let's go to a different model. Let's just go to this tree-net over here, and let's just say score. So this is the data that we're going to be scoring. I could change this to a different data set. So let's do that. Let's change it to this data set. So now we're using a different data set. Happens to be almost identical to the original one, but that's not an issue. What you just want to realize here is this could be any data set. Then this is the model that we're going to use to predict. Typically, you will want to save the results. So let's just give this a name. I'll just give it the name VVV. And what am I going to save there? Well, how about if I save everything? That is all the variables that are in the input data set, plus the predictions that are being made. So let's just score it. And now we see what our results are. The mean squared error here is so low because, of course, I have now been looking at the training data as well as the test data. If I were to open that data set now, what you will see there is that there are residuals, responses, and other variables that have been added to the data set. Going on to the next question. Rules are important, but a transparent model is also important. How would you go from rules to an intuitive model? Well, as I said, partly what an intuitive model is a function of what the organization that you're working with is used to. There are shops that are used to regression and logistic regression, and anything different is not transparent. There are other shops that have gotten so used to trees, and they find trees intuitive, and they find regressions and logistic regressions impossible to understand. Whether rules are helpful or not is going to depend on who those rules are being presented to and how. So I would think that there will be circumstances where rules may be ideal because in terms of deployment, rules are either the easiest or the only possibility. There's a question about how much data that we can handle. The answer here is the training data set needs to be loaded into RAM. That is one of the requirements of the engines that we use. In today's world, it's very easy to find yourself working on either a laptop that has 16 gig of RAM or a server that has hundreds of gig of RAM. That is going to be your limitation. There's also a limitation in terms of the licensing of the software. You may have a license that limits you to, say, 32 gig, or might be a terabyte. So long as you have enough RAM to load the training data, then we'll be able to handle that. In terms of number of predictors, the software is ready to go into the millions. We have sometimes run with data sets that have over 1 million columns. The last question that I see on screen here is, how do you identify the classification method which is best? Well, that's really that belongs in the next series, but let's just pretend that was, instead of classification, but best regression, because the strategy is really the same. We spend the first few hours of working with a new data set by running as many of the different methods that we have as we can. We often run them in the form of scripts. You can see here that I have a whole lot of commands. This is saved for you automatically after every session. And so I know exactly what I did in this session by referring to this particular command log. I'm going to close this now and show you, if I go to View, Past Session Logs, those are all my session logs. I have no choice. These are going to be saved for me whether I want them or not. You can delete them, of course. But this becomes a permanent record, if you like, of everything that you did. The nice thing is, if you realize that you did something 2 months ago and you're curious as to what you did, then you can just scroll back through this to find the session of that day or the sessions of that day, and there'll be an exact mechanism for reproducing what you did. There's a question about what is the minimum RAM. Well, I think we would go with, we're recommending that you work with Windows 7 if you can, if you're running in Windows at all. I personally ran XP until a year ago. That is the old Windows XP. I was a diehard. If you're working in those older environments, we strongly recommend 4 gig of RAM. If you're in a new environment, we recommend that you don't go below 8, just so you can take advantage of the fact that we have a 64-bit OS and a 64-bit application, and there's a lot of advantages from working in that environment. But technically, if you are working with small data sets, you could go lower. I think that we've now come to the end of our session. I want to thank everybody again for joining us. We do look forward to seeing you again, or having you participate with us in the future sessions, so please stay tuned, and please feel free to send us questions of any kind as you work with the software. Our goal is to make you as effective as possible in using these tools. Again, thank you very much and goodbye.